Rob, and this series of videos is going to be on the K40 laser and what I'm doing to upgrade mine and how to use it. This isn't a review, unboxing, whatever. It's, you know, there's enough of those out on the internet. It's just kind of a documentation of the process of me using this, learning it, and hopefully you can learn something from it too. The K40 laser, or so it's called, Chinese laser, bought off of eBay. I think I paid $350 with one important thing that does not come with it, which is a pair of laser safety goggles or glasses. Make sure you get ones that are rated for the actual band or wavelength of CO2 lasers. This isn't, you know, just your household laser. These are on a different wavelength and much hotter. Couple other things that don't come with it: a tank for your water. They give you a water pump. They give you some silicone hose, which is rather short. So, and you know, I picked up a 5-gallon bucket at the hardware store and some distilled water to run through it. So that's good. Another thing I picked up was a pair of calipers. Got these from Harbor Freight for less than $10. You know, they don't have to be fancy. They're really there more for just checking quick measurements. You're not going to be that precise with a pair of calipers anyway. So start out with what these are and are not. These lasers are not built top of the line. They are built down to a price. So they have limitations. They can put out really good quality results, but if you pay attention to those limitations and pay, you know, work within the limits of the machine, you can get great results out of the system. A couple of things I'm going to cover are how the system works, and that's what this video is primarily going to be about, the fundamentals of the system and how it works. The reason for this is that if you're going to upgrade your system, you really should understand how it works first, because you don't know if your upgrade is going to actually be an upgrade, or is it going to do the same thing, or is it going to be worse than the original state. So understanding how this system works is very important. So I'm going to cover the components of the system and how each one of them works and how they interact with each other. So let's take a look at first the components of the system. Okay, so first we're going to start by looking at the laser tube, which sits here in the back of the machine. It's about a little less than a meter long. On one end, down here at this end, there's actually a mirror, and up on this end of the tube there is a semi-transparent mirror. And the way the tube works is very similar to, say, a fluorescent tube. We have, you can see the wire come in right here on this end, a high voltage that comes through here and excites the CO2 gas in combination with several other gases, and that excitement of molecules reflects back and forth between those two mirrors until it's strong enough to leave the system. Once it leaves the system, it comes out here and it hits your fixed mirror. And that's, see, it's set at a 45-degree angle to the CO2 laser tube, and that reflects that beam into the print head. You can see the hole through the back there. It comes into the print body, and on the gantry there's another mirror at 45 degrees. So I'll slide this out, and that mirror reflects the beam over to your print head, which has another mirror set at 45 degrees angled down to deflect the image down into the system, and inside of this print head there's a lens that focuses that beam. And you can see we've got our gantry here that the print head moves back and forth on, and the gantry itself moves back and forth. So I wanted to show you in a graphic diagram exactly how the laser is working, because you can't see the laser. I did this little graphics diagram here so you can see what's going on. As you can see, we've got our CO2 laser tube back here, and it's shooting to the fixed mirror that I showed you in the machine. This mirror is fixed, it's not going anywhere, it doesn't move at all. It reflects the beam down to the gantry. Now the gantry itself can move up and down, and as it moves up and down, you can see the beam here gets longer and shorter, but continues to function and reflect off of this 45-degree mirror to the print head, which can move back and forth on the gantry and redirects the laser down. Now, when it does this, I mean, the important thing about this is that this is perfectly aligned, you know, the way this is set up. If you have an alignment issue, it's going to cause a misalignment like this. Now, again, we've got our CO2 laser tube here, and it's hitting the beam, and say this mirror is off a little bit, so the reflection's not going exactly down at 90 degrees to the original image. When the gantry is up closest to the laser tube, you can see the beam's coming down and it's hitting pretty close to the center of the mirror and probably being reflected where it needs to be. But as it gets further away, that beam eventually moves off of the mirror. This creates a problem. Same can be said here. If this mirror, the gantry mirror, is out of alignment, then we'll have the problem with the print head not getting. So as the print head's over here to the left, the beam is relatively well aligned to the center of the thing and being pointed down. As it moves to the right, that beam will traverse off. So aligning your laser is important. Now, I'm not going to go through the laser alignment process. There's several videos out there. If somebody wants me to, I will. It's not that difficult. The adjustments on these are not good. Possibly another future upgrade would be a replacement mirror holder that allows you to have a much finer adjustment. The current ones work, but aren't real pretty. Another key thing to remember about the light delivery system is that final print head. So as you can see, we've got our laser beam coming in here from the left. It hits our 45-degree mirror and redirects it down. Up to this point, it's a laser. Lasers, by definition, they have a parallel wave in their beam. It does not get narrower or wider over distance. So you have this beam. You know, I don't know exactly how wide it is, probably a couple millimeters. It's going to hit this mirror, it's going to reflect down, and then it hits the final optical component, which is your lens. And what this lens does is it creates a focal point where it takes that beam and focuses it down to a single tiny dot. You know, infinitesimally small dot is the theory. And these are different focal lengths. You can get different focal length lenses. Now, the one that comes with these is typically 50.8 millimeters, or exactly 2 inches from the lens to the workpiece is the finest point. Now, keep in mind that you may not necessarily want your product to be right at the top of it, to be right at that point. So, for example, let me put in a piece of material here. So, we'll throw in our piece of material. Now, if I take this piece of material and I want to engrave on the surface, I want to have that right at that focal point. So the pinpoint dot, the finest resolution, will be right at the surface. That way I get the crispest, sharpest marking. Now, if I'm cutting, I may want actually that focal point to be right in the middle of the piece. That way the sharpest point is here, but I've still got a very tight beam all the way down, relatively square sides. Now, if you have your focal length is way out, you know, say you're way low, your material's too thin, you're going to get a very fuzzy engraving, bad cuts, poor quality. If you have a very thick piece of material, same issue. You're going to be too close to the workpiece, your focal length is going to be out of place, and you're going to get fuzzy quality, bad cuts, poor power concentration. So something to keep in mind. And on another note, just be aware that these do get dirty, and they get dirty constantly. One of the advantages of an air assist is that it closes this and pressurizes this area and keeps your lens clear of materials. But until you have one, or even if you do have one, you need to check these on a regular basis. So any power that is not delivered to your workpiece is being absorbed by the material, and you can shatter a lens, break a mirror, and we will discuss that more in the mirrors video. And you see over here, you see just the gear on the stepper motor here is hidden underneath that plate, but this tooth belt and stepper motor is what moves your print head back and forth. It's not possible to see. I don't think I can get an image. Yeah. But the same thing is happening down here that moves your gantry back and forth. Underneath it, you see your materials support. Normally there's a clamp that's bolted right in here. I actually removed mine. This clamp is pretty useless. It's much smaller than the physical print area that's advertised. It's very sketchy in how it clamps anything. It's just not a good clamp. The other problem with this print bed area is that it's a fixed height, which means the focal length from your beam to this is fixed. If you put a thick piece of wood on here, then you're sitting too high. If you have too thin a piece of material, it'll sit too low. In addition, we have the issue with the giant hole in the center. Nice for letting stuff drop through, but not so good for supporting small pieces of work so they don't slip or slide while printing. There seems to be a lot of discussion and concern about the included software. There's 3 packages that came with my laser engraver. Laser Draw, which is a standalone laser engraving software. It does cutting, marking, and engraving, raster engraving. Corel Laser, which is included, however, does not include the actual Corel software, and that's where the disadvantage comes in for Corel Laser. If you have Corel Draw, Corel Laser is a plug-in for it that allows you to use the advantages of, the fully featured Corel drawing system and use that to directly engrave from the Corel Draw to your laser. And the third one is WinSeal XP. I haven't played much with this, but it appears it's mainly for raster engraving. It says it's for making stamps, seals, anti-counterfeiting seals, things like that. I haven't had any real need to use it and haven't found the place where it fits. I've primarily used Laser Draw. I've also used some open source software. There's a plugin that you can get for Inkscape that allows you to use the fully featured Inkscape environment and then export Laser Draw files. So it makes for a good compromise between those two. So again, a lot of people you might ask, what's the problem? Why do people complain about the software? The biggest reason is it requires USB. It's a copy protection mechanism. There's a little USB dongle that I showed you that is required to be used to make the software work. That's not uncommon in the professional industry to have a USB dongle type copy protection. The other reason is the help and the abouts, things like that. I've got it installed on here. There is a language barrier. It's clear the person that wrote this software does not speak English natively, and a lot of this is translated with people using Google Translate or whatever automated tools. So the grammar becomes a little hard to understand. The people that complain about that, I would ask them to do the same. Take their native language, say it's English, and translate what you say to Chinese and do a good job of it without knowing Chinese. I give them the benefit of the doubt there. Another possible concern is it does show up. Antivirus scanners do complain that this software might cause problems. Due to this, I actually installed mine on a virtual machine that I run on my system. That's how I do most of my software anyway. But I haven't seen any real problems. There's no indication that it's doing anything bad, or it's just that it was compiled in China and antivirus software tends to complain about things like that. So other than that, the software itself works fairly well. So like I said, I use primarily Laser Draw. You can build stuff directly in Laser Draw. You can go in here and you can put shapes and text and all of that directly from here, or like I said, I've been using a plugin for Inkscape, a free open source vector graphics tool, and used it to create the Laser Draw things, and then I go into Laser Draw just for the engraving itself. As I mentioned earlier, I picked up a 5-gallon bucket from a local hardware store. I also picked up some additional tubing so I could move this a little bit further away from the main machine. I drilled some holes in this lid, which is fixed on here very good. And inside of here is the supplied pump. Again, the quality of these materials probably not the best. Should be double insulated pump. I wouldn't stick your hand in that water while the electricity is turned on to it, unless you're in for a shocking experience. Additionally, one of the things they supply is your ventilation. Now again, I've already replaced this tube. Nothing really wrong with the original plastic tubing other than it doesn't collapse back easily. And I needed it to collapse back because I need to be able to put it out my window for cutting and then put it away and close the window when I'm not cutting. We've got a small 2.5 cubic meter per minute fan here. That's about 80 cubic feet per minute. And that's what ventilates, and it draws exhaust, smoke and stuff into this pipe or here, which is one of the problems, that this is actually too far forward and it takes up some of your print area. So this may get trimmed back so I can gain a little bit more print area out of the system. So on the controls side of things, this is where a lot of them vary, is depending on what's on this side of the system. Mine's pretty basic. We have a potentiometer that sets your power level, a milliamp meter that's set so you can read what the power level is, a laser safety switch that allows you to disengage the laser, a test switch so you can fire the laser manually, and a power switch to turn it on and off. Inside of this we have our laser power supply. This puts out 24 volts up to 1 amp, and also puts out the approximately, I'm guessing because I can't find any specs on this, probably around 20,000 volts to the laser tube. That's what they seem to be spec'd at usually. And up on the front here, let's see if I can get a view of it, is our control board and the USB that runs it, USB cable. This is what drives your stepper motors. These are proprietary boards. They use a proprietary language, and that's one of the things that a lot of people complain about. It does work, nothing outright wrong with it, but it is kind of annoying. You also, you have this little USB dongle that you have to put in your computer every time you try and print, otherwise it won't talk to the software. And there's also a sticker on here that has the serial number of the board that you have to put into the software so it recognizes it and makes it work. That's all that's in here. There isn't much. It's very straightforward, very simple. That leaves us a lot of room and a lot of options for upgrades and improvements. So this brings us to a couple of safety pointers. The first one we're going to point out, and the safety risk that we have in here, is high voltage. We have live mains voltage down here. In the US is 120 volts. Substantial amperage, enough to seriously hurt you, if not kill you, if you hit it wrong. We have 28,000 volts, or roughly, in the tens of thousands of volts at least, feeding this CO2 laser tube. The amperage is very low, but that voltage is enough to put your heart into a bad state if you were happen to get it in the wrong place. So keep your hands out of the machine when it's powered on. This one's currently powered off and unplugged, so I'm not worried about it. The second thing to be worried about, or to be aware of, not worried about, but aware of, is your laser light. Now, as you saw, the way the laser comes in, it bounces off this mirror and bounces off this mirror. These areas in between here, there is a laser traveling through there, and you cannot see it. It is invisible to the naked eye. But it is definitely going to hurt if you get your hand in there. This is serious energy. If you work this with the lid open and you don't choose not to put a safety switch on the lid, get laser safety glasses. Protect your eyes. The damage that will be done by this will be permanent. And the third thing to be aware of is mechanical motion. These are not particularly strong stepper motors, but you do have mechanical motion. There's pinch points in here. You can get your finger caught in things. So keep your hands out while it's moving and be aware of that at all times. Another piece I'd like to cover is documentation. I created this laser cutting logbook, or laser engraving logbook, whatever you want to call it. I picked up a clipboard. This is 8.5 by 14 in the US, so US paper here. And just gives me a date, job description, the material that I was cutting, so I can tell what it was and how thick it was, and what settings I used. This is particularly important to document your successes and failures, and be able to go back and look and go, I know I engraved this material once before. What was the setting that worked the best for it? If you don't document this, you're going to be thinking, I'll remember it, but in a year you'll be trying to do something and be, wondering, well, what was that? And as I fill this out by hand while I'm cutting, and then later on I go back and transfer it into my computer, and that way I can do searches on it and keep track. And I have a few sheets here, so I don't have to keep going back. You can see some of these are printed because they were entered in the system. But documentation of your work and documenting what you're doing, how you're doing it, when you're doing it, what maintenance you do. For example, cleaning the mirrors, which is going to be a critical thing that you got to keep up on. Making sure those mirrors and lenses are real clean. We'll discuss that in the next video when I talk about the mirrors themselves. So now I'm going to start into talking about upgrade plans. One of the first ones is the upgrading of the duct. I've already done this. I've replaced this ducting with a dryer hose, much more flexible, easier to work with. I do plan on upgrading this fan and moving to an inline fan on the end of the hose, so the hose is always under suction, not under pressure, so that way you don't push any exhaust gases out a hole into the room. And replacing this fan with a, this fan slots in, you can see here. It slots into this little groove. And it doesn't fit particularly tight. I tape it up, but it's just very bad fit. I'm going to make an adapter that slides into that groove to attach to the hose, and then put the inline fan at the end of it. As I mentioned earlier, the other thing I was going to change, and this is because when this thing zeroes, it comes back, it hits its switch, and it comes back just off the switch. So all of this area, you can see this laser has probably got half an inch, maybe 10 millimeters, 20 millimeters of space that's being taken up by this duct that could be printable area. So I'm going to trim this duct back to be behind that, so it's not taking up valuable print area that we could use. So another upgrade that I'm going to do is, you can see at the back of my laser here, they included this little LED light strip, which is nice. It gives us some light underneath the deck. However, because it's behind everything back there, it tends to create shadows on your work. It makes it difficult to see, and it kind of encourages the, hey, let's open the lid and see what's going on, which is bad for ventilation as well as potential reflection into the eyes. So my intention is to add a couple of lighting strips on either side of the mirror or viewport here, pointing down, and I'll have connectors so I can still remove my lid when I need to, so that we can have a little bit more downlighting on what's going on, and maybe potentially put a camera inside of the case to be able to monitor it from the outside or from remote sites. Another upgrade I'm going to do is adding air assist. Now I've got this little 3D printed nozzle, and I need to get an air hose and a pump that's appropriate for it. This will fit up underneath here, and it attaches to the print head, and it basically puts a little jet of air. The reason for this is to basically, it does a couple of things. One, it drives the smoke away from the path of the laser. Anything that gets in the way of that laser, smoke, reflection, material, can limit its power. It diffracts that image or the laser light and doesn't get to your workpiece. Additionally, with a little bit of pressure behind it, it'll help the burning process when burning through wood and materials, so it gives it that little extra oomph to get through thicker materials, produce a cleaner cut, less charring. So that's an important upgrade. I need to get an air pump and hose that fits this and has the flexibility to track with the head and all of its locations without getting in the way. As I had pointed out earlier, one of the biggest problems here with this table is its lack of adjustability, that and the big hole in the center. My intention is I'll replace this top deck with a expanded metal material that gives me a nice surface with lots of little holes in it to let gases and pieces fall through, but yet still gives us good support under the work, and then put in an adjustable Z-height table. That way I can come in here, and I probably will not put it on a stepper motor, but I will give it a manual crank control so that I can raise and lower the head as I need to and keep everything in line keep it all level, but be able to adjust for different thicknesses of material, because that focal length is very, very important, as I showed. So another improvement I'm planning on making is replacing the control board, the proprietary control board here, with a open source, open standard control board that one of two options I'm considering is either a ramps board or a Arduino CNC Shield version 3. Between these two and the Garble or Gerbil code, we can control this with an open standard, well-known protocol called G-code that CNC machines use in most cases, allowing us a little bit more flexibility in building jobs, being able to engrave and cut in one job, things like that. So that's one of the improvements I'm planning on making. Now the control panel here is very simple. As I showed you, we have a milliamp meter and the potentiometer. I've done some testing and I can show you the results of this, but basically this potentiometer is very, very inaccurate. I added this scale on it so you'd have some reference points, but I can set it to 70% and one time, set it to 70% next time, and just being a hair different, and it can change the milliamp draw drastically. So I've actually changed, now I document, I do a test fire and document what I'm actually driving at milliamps rather than what this is set at, because this is so inaccurate. But because of that, I want to add a monitoring system that tracks the voltage coming off of the potentiometer, or preferably with the G-code upgrade I'm going to do, I would like this to be pulse width management, pulse width modulation coming off of the G-code controller that adjusts the power level of the laser so it can dynamically adjust its power. But in addition to that, I want to have a separate Arduino that's running a monitoring system that's tracking water flow, water temperature, current power settings, and things like that allow us to monitor and track those items, and give us a little bit tighter control over what's going on. As part of that, I want to have a water flow and water temperature interlock built into that, so that if the water flow were to stop or the temperature were to get too high on the water, that it would actually shut the laser down to protect it. The reason for this is, the cooling system on this is very basic. We've got a pump, a couple of hoses here going into a bucket, and it's not a very good pump. If it fails and that laser's running without cooling, it's very likely that it will last only a few minutes before it completely gives up. So we want to have an interlock that protects and shuts down that laser in the case of a pump failure or water temperature getting overheat. So one of the safety pieces I want to add to this is a lid switch or lid interlock switch that would protect, this is a micro switch I pulled, I pulled this out of a microwave, but have this set up so that when the lid is closed the laser will fire, but when you open it, it shuts that laser down. This can can interfere with, people want to have this lid open for filming or just because it's easier to see. I think the safety aspect of this is more important than being able to see what's going on in here. The laser does its job. It doesn't need to be monitored, doesn't need to be babied. So protect your eyes, and so I'm going to add a laser interlock switch that when the lid is open the laser will be disabled. Not sure if I'm going to put it back here where when the lid closes it'll close that, or maybe on this side where if the lid closes it'll close the switch. Either way, haven't decided, but that's the plan, is put a lid interlock switch in the system. Another problem I found with the laser is being able to target it, to know where you're going to start your print. You put a piece of wood in here, put a piece of glass in here, whatever it is that you're going to cut, and you try and target that laser, and all you can do is hit the test fire switch, but that can actually damage the workpiece that you're working on. So what I want to add is a targeting laser. There's a couple of ways that I've seen this done. You can add components to this where the laser's pointing down and it targets on the wood. The problem is that if you point this at an angle and your focal length's different, you don't necessarily know that's exactly where your beam is going to hit. You're getting close but not perfect. A better way of doing it is to put another mirror slash lens here it's invisible to CO2 laser, but reflective to red laser. So then you would have a red laser pointer here that would point, reflect, and get into the actual beam path of where the CO2 laser is going. Now this is the better way of doing it, however much more expensive. Those one-way reflective mirrors are very expensive, on the order of 70 or 80 bucks. So we will see on that. Is not the most critical item. One of the tricks I've done now to help that is I've got this board in here that I've cut with the laser to my 0 point, so I know that this is my 0 point. Actually, my 0 point's up here, but I know exactly how far this is down, so I can set my workpiece on the laser burning software from there. I hope that this introduction to the fundamentals of the K40 laser system is helpful to others. In the next video I'm going to do, I'm going to cover the mirrors that are used inside of these machines and the lenses. These aren't your typical mirrors, so you have to treat them carefully, and you can't just pick one up at the corner store. So hope this has helped. Let me know in the comments if there's anything you'd like me to talk about. Otherwise, I will talk to you later.